Hi, I'm Wang Tao. I will be talking our work, Direct Multiview Multi-Person 3D Human Pose Estimation. This is a joint work with Jianfeng, Yujun, Shuicheng, and Jiashi. 3D Human Pose Estimation aims to estimate the 3D body joint locations from the input image or video. It benefits many real-world applications like sports analysis, gaming, and mixed reality. 3D pose estimation from multi-view images has been a popular research field is a multi-view inputs can help address the limitations in molecular input, like the self-ambiguity due to perspective projection and the self-occlusion of body joints. It can thus more accurately estimate the 3D body joint location. Previous works mainly adopt two common approaches. The first is volumetric approach. It first estimates the joint heat maps for each camera view, and then project those heat maps into a common 3D space. The 3D confidence cube is then integrated to get the 3D pose. The reconstruction approach first detect 2D pose for each camera view, and then use the 2D pose to reconstruct the 3D pose, usually through some method like triangulation. In this work, we focus on the more general multi-view, multi-person 3D human pose estimation. So given the synchronized multi-view camera inputs and the corresponding camera parameters, we aim to detect and estimate the 3D pose of each subject in the scene. The existing works can be viewed as extension of the single-person methods. The first is voxel pose. It builds a two-stage object detection alike pipeline on the volumetric representation. So it first estimates the proposals for the center location of each person in the scene. Based on the proposal, it constructs more fine confidence volume for each proposal and integrate this confidence cube to get the 3D pose. The second approach is multi-view matching. It first detects 2D poses for each camera view, and then perform cross-view matching to find the 2D pose for same-person cross views. With the grouped 2D poses, it then reconstructs them to get the 3D pose of different persons. The volumetric approach and the reconstruction-based approach have their own limitations. First, they are multi-stage, and thus is complex and not efficient. Second, they depend on intermediate 2D tasks, which suffer from occlusion. Also, method like reconstruction-based approach and suffer from the noise in the cross-view matching procedure. And the 3D volumetric representation is costly in computation and memory, and it can also lead to quantization error. So we want to ask, can we directly regress the 3D pose from multi-view images? In this work, we designed a multi-view pose transformer model to achieve this goal. In short, this model is called MVP. So we model each body joint as a joint query and directly regress the 3D body joint location from the multi-view image feature. The joint queries can be seen as learnable embedding vectors. Here is an overview of MVP. It adopts a multi-layer decoder to regress the 3D joint location. Given the initial joint query and 3D joint location, each decoder layer updates the joint queries and refines the 3D location from previous layer by attending to the multi-view information. The joint queries are grouped to represent the body joints of different persons. So how to construct those joint queries? The most naive way is to use per joint queries. That is, we use independent query embedding for each body joint. But we find this scheme does not generalize well because the joint queries are independent and cannot share the joint level knowledge across different persons. So we design a hierarchical query embedding scheme. We have a separate set of person level queries and a set of joint level queries. We hierarchically aid them to get the whole set of joint queries. Here is an illustration of the hierarchical query embedding scheme. So the joint level knowledge can be shared across different persons, while the poses of different persons can be differentiated with different person level queries. The number of learnable parameters is reduced from n times j times c for the naive per join query scheme to n plus j times c for our hierarchical query embedding scheme. From another perspective, this scheme can reduce overfitting to training data and helps the model generalize better. The problem with the joint query is that they are static. That is, they are learned from data and are not aware of the input images, and thus may not generalize well to the test data. So we propose input-dependent query adaptation scheme. We augment the above joint queries with a globally pooled feature vector. In this way, the joint queries are adaptive to the input image feature and can thus generalize better to the test data. Um, the next question is how to aggregate the multi-view information. So we can naively adopt the dot product attention to densely attend over the multi-view image features. But the problem is it incurs enormous computation cost. To address the limitation, we propose projective attention. It is geometrically guided to fuse the localized feature information in each camera view. So given the current joint query feature and the current prediction of the 3D joint location, the projective attention first project the 3D location onto each camera view and gather the localized context information with a deformable operation. Formally, the 3D location is projected onto the camera view with the corresponding camera parameters, and then a learnable offset is added to this projected location. The features at the offsetted location are aggregated with an attention weight to get a feature information vector. The features are aggregated over different camera view to get the final projective attention result. And up to now, the projective attention does not consider the positional information. We know in transformer, the positional encoding is an important component. It provides the positional information of the input sequence. So how to encode the 3D multi-view positional information into the multi-view features? We use the camera array to achieve this goal. The camera array can be calculated with the camera parameters. It can represent the 3D dimensional information that each image pixel is captured from the camera. We concatenate the camera array to the image features and use a convolution to fuse them into a new feature. We call this operation reconf. So with reconf, the projective attention is augmented with strong multi-view geometric information and can thus help more accurately estimate the 3D joint location. Here is the overall architecture of the model. So each decoder layer consists of self-attention and projective attention and feed-forward layers to regress the joint location and predict the joint confidence. So how to train the MVP model? Given the law predictions of each body joint, that is the set of joint locations and the confidence score, we first group them to obtain the pose of different persons. The confidence is the average of the grouped set of confidence of the joints. So then we match the predicted pose to the set of ground truth pose. We first find a best permutation or a best match with a Hungarian algorithm. For the matching cost, we consider both the confidence of the prediction and the closeness of the prediction and the ground truth pose. Um, with the best match, we then compute the training objective for predicting the joint confidence and the regress of the 3D joint location. We sum the objective over different decode layer to get the total objective. For inference, we simply group the raw joint predictions to get the pose of different persons and use a confidence threshold to filter the negative predictions. We also extend MVP to predict the dense body shape. We simply perform average pooling on the joint level feature to get person level feature, and use a feed-forward network to predict the body mesh represented by a parametric SMPL model. So here is a qualitative result on panoptic dataset and result on shelf and campus datasets. Here is a result of quantitative evaluation on panoptic and the shelf and campus datasets. For panoptic dataset, we use average precision metric proposed from the VoxelPose. So we observe for the most strict AP25 metric, MVP significantly outperform VoxelPose, and the MPJP is about 2 millimeters lower. This indicates that the pose quality of MVP is much higher than that of voxel pose, and also the inference time is much less. On the shelf and campus datasets, our method also achieves comparable or better performance to the state vards. We also visualize the projective attention and self-attention. We observe the projective attention attends to the surrounding area of the target joint. For example, the projective attention on the middle hip attends to the waist and thorax across the different camera views. For the self-attention, we use more opaque color to represent stronger attention. We observe that for the self-attention on the body joints, it mainly attends to the other joints of the same person, and it also slightly attends to the other body joints, but with much less attention. This phenomenon is reasonable, as the body joints of the person are strongly correlated. They are subjected to strong priors like the body pose and the bone length. Here is the scalability with respect to the number of subjects. We observe MVP maintains almost constant inference time regardless of the number of persons. Even with a 100-person model, the overhead is very small over that of 10-person model. While for voxel pose, the inference time increased linearly with the number of person instances. We also perform various ablation studies to better understand the method. For example, without reconf, the performance is inferior. This is because the model have no access to the 3D multi-view geometric information, and thus cannot generalize well and cannot accurately predict the 3D location of the joint. Um, and for the different query embedding scheme, the hierarchical scheme significantly improves over the naive per joint scheme, and further aiding the dynamic adaptation can further improve the performance. We also perform other ablations on the uh, inference threshold and the number of decode layers and the number of camera views and the number of deformable points in the projective attention. For more details, please refer to our paper. Here comes a conclusion. MVP directly regrets the 3D body joint location for multi-person from multi-view images. It delivers several advantages. First, it is simple and easily extendable to other tasks like pose tracking and hand pose estimation. Second, it offers better scalability to large scene with many persons. And also, it potentially may benefit from more large-scale datasets with diverse pose distribution, as MVP is an learn-to-learn and learning-based method. We also observe some limitations, like the cross-view or cross-camera generalization, that is training on one set of cameras and generalize to another set. We will explore in the future for methods like disentangling the cameras and the feature representation learning to better address those limitations. So with that, I would like to end my presentation. Thank you.